Okay, last time we looked at the simple equations that you get when you have non-interacting quantum particles in a box or any set of energy levels, really. And what we found out was that the number of particles in some kth energy level, okay, on the average looks something like 1 over e to the energy of that level minus some chemical potential divided by K Boltzmann times T plus or minus 1. Okay, so plus 1 is for the fermion case, minus 1 is for the boson case. Okay, so that's the average number of particles you expect to find in an energy level with energy Ek. Now, how did we arrive at this? Remember, we had two Lagrange multipliers. Those two Lagrange multipliers were used to adjust the average energy, okay, and the number of particles in the system. Okay, so the two Lagrange multipliers, this temperature T, okay, adjusts the average value of the energy of the system, okay, and this mu adjusts the average number of particles. Okay, so in fact, I should put it like this. Okay, what is n? Average value of n is the total number of particles in the system, so it's going to be something which looks like, okay, nk. Okay, so I have nk, small nk particles in the kth state. Okay, if I add them all up, that's what I get. So if what I do is I adjust this mu in order to get the number of particles that I want in the system. Now, if I have a problem in which I don't want to adjust the number of particles, for example, I don't really care, or conversely, if I know the number of particles in the system, so I am going to use that n, then in that case, I don't need this chemical potential, okay? That's the Lagrange multiplier which adjusts the number of particles. Then you set it equal to 0, okay? It doesn't appear in the maximization equation. Remember, we had this maximization equation which we said, okay, I want to maximize this pk, ln pk, okay, and then we had a number of variables here which looked like, okay, some lambda 1 minus some pk, okay, so that when I differentiate with respect to lambda 1, I get certainly 1, okay, and another constraint, lambda 2, remember this was associated, we associated this with temperature. This was something like, okay, I want the average energy of the, I want to set the average energy of the system to, okay, Ek, Nk, okay, and Pk, really, okay, so expectation value of the energy. And then I had this lambda 3, which said, okay, the average number of particles, I want it equal to, okay, Ek, Nk. Okay, something like that. Okay, so this was associated then with mu. And I found the extremum of this, okay, last time, okay, using these variables to obtain a probability density function. Okay, so not probability density function, a probability function. Okay, so probability of having nk particles in a certain energy level was proportional to e to the minus energy of that state, which was epsilon k over kBt. Okay, and then I also had this plus mu over kBt, which was, okay, multiplying this for each particle. Okay, in fact, there's an nk here, right? Okay, so something like that. So now if I don't want any constraints on the number of particles, then I don't want this term. Okay, let's put equal to setting mu equal to 0. Okay, so that means this is just going to disappear. Okay, that is the case when I am not interested in the number of particles. Either I don't want to set that equal to something, okay, or I know what it is and I want to use that particular number. So let's look at an example of both types of systems. A nice and useful example of this is known as the blackbody radiation. You may have been exposed to this before, but let's go through it again. So what is a blackbody? A blackbody is some some object which absorbs all radiation falling on it. Okay, but from thermodynamical considerations, we know that it must also be emitting energy. Okay, so if you have two black objects, okay, so suppose you have one black object there and another black object there, okay, and you put them into some isolated space, okay, which cannot have any energy transfer from the outside, so it's a nice reflective wall, so that the electromagnetic radiation that comes out from one of them goes to the other one. Okay, so the second law of thermodynamics says that if whatever temperature you put these things in, they will come to some thermal equilibrium. Okay, so they will eventually reach an equilibrium where both of them will have the same temperature. So then you can argue that they must have the same spectrum, same energy spectrum. So all black objects must radiate with the same, okay, wavelength distribution. If there is some wavelength, there is some mismatch in the wavelength distribution. Suppose this is radiating a little bit more in red, and this is radiating a little bit more in the blue. Okay, so let's just schematically do something like that. Okay, so suppose this is radiating a lot in red and, okay, and not that much in blue. This is radiating a little bit in red and more in blue, right? So something like this. So what I can do is I can put a filter here, okay, which reflects, for example, red light back, okay, and passes the blue light. Okay, so you are going to get this red light being reflected. I'm obviously exaggerating this. This only needs to be a small amount. Okay, so this red light is reflected, but the blue light just passes through. Okay, so you see there's more energy going this way than energy coming that way. That would then increase the temperature of this object and decrease the temperature of that, which is against the second law of thermodynamics. So this was actually pointed out very early by Kirchhoff, the same Kirchhoff that made these circuit laws and everything. And he said, okay, all black objects must radiate with the same spectrum, and it was a challenge for physicists to find out what's happening. So what happens is you construct a black object by something like a cavity. Okay, you shouldn't make it perfectly spherical. The more irregular it is, the better. But if you now look at if you just punch a hole here and just look at this hole, you see any light that hits that hole is sort of absorbed. It goes into the hole and disappears. And some of the radiation that's inside will actually come out. So this is as close to an ideal black object as you can get, because not all black objects that we see around us are really black. Okay, it depends on the lighting and such things. Okay, so there's this interesting incident that when studio lights were converted from one type of lighting to another type of lighting, which contain more ultraviolet, more bluish color, which you don't ordinarily see. Okay, but these visitors, speakers in the studios, people started discovering that they were wearing socks with different colors, because in the morning they think they are both black, they wear them, but under studio lights they look different. Okay, so constructing an ideal black object is not always easy, and this is one nice way of doing it. Okay, so what we'll be doing is now we'll just try to look at it and analyze this spectrum. Okay, we'll again idealize this as a cubic box. Okay, because it's easier to make calculations, although you could use obviously other geometries. But we are going to get inside this cavity electromagnetic waves, which will be forming standing waves. And those standing waves have the same sort of structure as the electron waves that we discussed earlier. Okay, so there will be these boundary conditions. And if we look at those boundary conditions for the electromagnetic waves, again, they have to go to zero at both boundaries. So you can just choose pi L over, pi, okay, let's choose 2 pi over L x for the Kn, okay, wave number with periodic boundary conditions. Okay, so if I have periodic boundary conditions, remember I have a choice. I either use periodic boundary conditions or I use hard boundary conditions. So you see I have the same sort of structure for all of these waves. So what that means is I'm going to get in this K space, again, a mesh going in both positive K and negative K. So this is going to be Kx, Ky, Kz, and each point on this lattice, okay, so again, if I just go up here, come this way, go up by a certain amount, so this point is Kx, Ky, Kz. Each one of these points will support an electromagnetic wave, okay, with a certain periodicity in the x direction, a different periodicity in the y direction, and another one in the z direction. Okay, so I have this Kx, Ky, Kz. In the case of electrons, we said, okay, we can put two different types of spin particles per such a state. Also in the case of photons, okay, which will now be associated with these electromagnetic waves, I can put two different types of polarizations per, okay, state. So photon will be traveling in a certain direction. Its polarization can be either, okay, circular in one direction, circular in the other direction, or equivalently, okay, in one axis perpendicular to the propagation direction, or in the other axis. Okay, so there are, again, there is some not spin degeneracy, well, okay, polarization degeneracy. I can put 2 photons per state into each one of these things. Now, why am I talking about photons? You see, this is an electromagnetic wave, and if you look at the energy, okay, you remember from electromagnetism that you have the energy structure which looks like epsilon 0 over 2 electric field squared plus 1 over 2 mu 0 magnetic field squared. So you have these two quantities which contain the energy, and you can transform this into a problem of harmonic oscillator. Okay, so we are not yet equipped to do this, but just remember that I had 1 over 2 m v squared or p squared over 2m, okay, p squared over 2m for kinetic energy plus 1 over 2 kx squared. Okay, potential energy, again, squares of these two terms, and but in a similar vein, I can analyze these modes as if they are harmonic oscillators. Okay, so I'm going to get a harmonic oscillator for each one of these points. Each one of these points will correspond to a harmonic oscillator, and we'll analyze them as if, okay, they are mechanical oscillators and see what happens. Yes?
Could you please explain how the cavity approximates a perfect black body?
Okay. What we assume is that if we have this cavity and we punch a hole on the surface, okay, any photon, any light that gets in, strikes these walls, okay, does some random motion, etc., so that it's lost. Okay, now it is important that we keep this thing at a certain temperature, which means, okay, so from statistical physics, what we mean by keeping it at a certain temperature is that this is in contact with a heat bath at a certain temperature. So you have a nice, massive object at a certain temperature, so that you can have energy fluctuations between the cavity and this source. So that means these photons which are moving around at certain times are absorbed by this wall and impart energy to the heat bath, and sometimes this heat bath, because it's moving the surface, okay, atoms, it generates a photon associated with that temperature. Okay, so although that part of the mechanism is quite complicated, the nice thing about the statistical look at this thing is that I am not really interested in the details of how this energy transfer happens, as long as it happens. Okay, as long as I keep it at a certain temperature, I know that these photons will sometimes disappear, sometimes will be created, etc. But we are going to just look at the statistics of the photons at that temperature. So the reason this appears to be a black object is because any light that falls on this hole is lost, okay? It doesn't come back. But of course, the photons that are inside this cavity also escape from this hole, so that makes up the radiation, okay? All right, any other questions? All right, so that's the structure of the problem. Now I have a bunch of states here, and those states are all going to be occupied with some probability with n number of photons. Okay, so I'm going to get n photons in this state, okay, which corresponds to certain energy. So it's going to have some energy Ek, and that occupation will be given by that equation. So let's just look at again the energetics of this. I have this k squared factor, which is going to be kx squared plus ky squared plus kz squared. And I know that the magnitude of this h bar k, remember k is 2 pi divided by the wavelength, okay, whether it's an electron or a photon, it doesn't make any difference. K is 2 pi, okay, divided by the wavelength. Okay, so if I multiply it by h bar, I get the momentum. But unlike a particle with a mass, since this is moving with speed of light, the energy of the photon is just proportional to the momentum. Okay, so how do I go from momentum to energy for a photon? Times c, right? Okay, so the energy of the photon is just c. Okay, so this is the energy of the photon with with momentum p. By the way, this relationship, okay, in which you have the energy is proportional to the momentum, okay, is not limited to only relativistic particles. Okay, you have this now new fashionable amazing material which is called graphene, two-dimensional object in which the energy is proportional to momentum. Okay, not with speed of light, but there's some proportionality constant. Now, because of that, okay, you have all of the mechanisms of relativistic quantum mechanics, the Dirac equation and everything, which you can apply to this material. So it is theoretically and experimentally a very interesting type of material. Okay, so you'll hear Dirac equation being applied to graphene, etc. And some people automatically assume that there must be relativistic electrons moving around in the object. That's not the case. Okay, it's just that there's this relationship between the momentum and the energy. Okay, so this is the energy also is equal to h bar times omega. Okay, so I can represent the energy of the particle by its wave number or its momentum or its frequency. Okay, so those are all equivalent. Yes?
In graphene, all of the energy bands are proportional to momentum, or some bands?
No, well, I don't know if all of them, but the ones which are interesting, which corresponds to conduction of these electrons, have this form, at least to some amount of some range of values. Okay. Okay. So now that I have all of this, let me just put everything into this equation. Now, let me just look at the term Nk times the energy K. Okay, so what will that be? Well, that's going to be equal to, okay, I have the expression over there. Now, you see, I'm not going to even use the mu term there because I'm not interested in counting the number of photons in the system because the temperature will automatically generate a certain number of photons, which I can evaluate later if I like, but Okay, that's not the most interesting quantity. So I have e to the ek over kBt plus 1, because I have photons. And then I am going to multiply this by 2, okay, because this is, if you like, the polarization degeneracy. So I'm going to get 2 parts. Maybe I'll put that, okay, so I have to put it somewhere, but maybe I'll put it into the counting process with the k's again. Minus 1, thank you. Very important, yes.
If we are working with bosons and they can occupy as many same, why do we have a multiple of 2, just 2 in the K space? And
okay.
More than 2,
no, you can have more than 2, but you have 2 states, so it's just counting the states. For a certain kx, ky, and kz here, okay, I have really 2 states, one state corresponding to, okay, say up-down polarization, the other one corresponding to left-right polarization, okay? Okay, so that's our nk, and ek is going to be equal to, okay, c h bar times k. Okay, so that is the energy corresponding to one of these states with a certain polarization. Now I want to find the energy density corresponding to various wavelengths, various values of k. Okay, so now each one of these things is, okay, so we know how to count these things. By the way, this ek is also becomes c h bar k now. I do the same sort of calculation that I did earlier, okay? So this, define the number of energy states inside this box between k and, okay, k plus dk, okay? So the number of states which are between some value of k and k plus dk is going to be equal to what? The area of this sphere, which is going to be 4 pi k squared, right, times dk.
Over 8.
Okay, over, not 8, because I have used periodic boundary conditions. Okay, so the mesh, okay, the mesh here is equal to 2 pi over L. So I'm going to get 2 pi over L cubed here, okay? So effectively, I still have the 1 over 8 hidden there. Now I put in the polarization degeneracy, okay, factor of 2. So these are just the number of states, their energies, and this is their average occupation. You see, this can be more than 1. Okay, in fact, for the lower energy states, for small ek, this is going to be larger. Okay, for higher energy states, obviously, this just goes down exponentially. So it is quite a good cutoff, okay? And that's one of the successes of quantum mechanics. So if you use classical mechanics, the energy distribution here, well, it's a different story. You probably know what happens in classical mechanics, right? You've heard of the equipartition theorem?
Yeah.
Okay. Okay. In classical mechanics, there's a equipartition. Okay, so let me just write it down. Okay, perhaps we should say classical statistical mechanics, just says that average energy of a harmonic oscillator is equal to k Boltzmann times T. Okay, this is called the equipartition theorem. Okay, so this just says that if you have a harmonic oscillator, each one of these things, so you don't have to look at the energetics of each one of them is going to have a kb times T amount of energy associated with them. So you have an infinite number of oscillators going into higher and higher frequencies. Each one of them is going to have energy k Boltzmann times T. So effectively you have infinite amount of energy, which caused a dilemma in the calculations. But okay, so quantum mechanically you get this exponential factor which kills the result. Yes.
And what does this whole expression equal to?
What is this equal to? Okay, so if I integrate this over all dk, 0 to infinity, that will give me the internal energy. Okay, so it's going to give me a sum over all of the states, okay, with their energies. So that's the energy of the system. That's the number of particles inside that system, and this is the number of particles between k and k plus dk. Okay, so if I add them all up, I get the total internal energy of the system. Okay, but what I am going to be interested is this piece inside the integral, because that gives me the distribution of energy to different frequencies. So if I now go back over here and look at what k is related to omega, okay, frequency of oscillation with a factor of, no, not h bar c, right? Omega over c. Okay, this just relates wavelength to frequency. Okay, so that's that. So I can convert this into an integral. Okay, so I can write this. Let me just write the integral again. What I'm going to do is I'm going to make a transformation from k to omega, so that wherever I see a k, I am going to put in an omega over c. The ek over here is equal to okay, c times h bar k. Okay. So let's just do that. If I now put in, okay, help me with the algebra. So integral is still from 0 to infinity. And I have here a factor. Let's see what that is. That's 8 over pi squared, right? K squared dk multiplied by the volume of the system. L cubed is the volume of the system. So let me just write that down. Write that down for first. 8 over pi squared, okay, k squared dk. Now in place of k, I'm going to put omega over c. So omega over c squared. dk is going to be d omega over c. Okay, yes?
1 over pi squared.
1 over again?
You wrote 8 over pi squared.
Yeah, okay, I'm sorry. This is 8, right? Okay, thank you. Okay, what else? Okay, so where am I? There's a C h bar k. So if I put k equal to omega over c there, I am going to be left with just a single h bar. Okay, and then I have this exponential factor, which is going to be I'm doing things.
This can be omega over c.
Yeah, so omega over c, which means I'm going to get another factor of omega here, right? So h bar omega is the energy, right? So this thing is, as we might expect, is equal to h bar omega, right? And then I have 1 over e to the h bar omega over kBt minus 1, okay? So I think I got all the terms in. All right, so I have something like this. Let's just simplify it a little bit. Let's just pull out the constants and such things. So I'm going to get h bar over c cubed pi squared.
You forgot V.
You forgot what?
V.
Oh, yes, the volume. Thank you. So so the energy of the black box, the total energy inside is proportional to the volume, as you might expect. Okay, and then I have a omega cubed d omega divided by e to the h bar omega over kBt minus 1. Okay, 0 to infinity. Okay, so what you can do now is interpret this thing without the integral as some sort of energy per frequency. Okay, so if I just look at that part, so h bar times v divided by c cubed pi squared times omega cubed over e to the h bar omega over kBt minus 1 is the energy, okay, in the system between omega and omega plus d omega, right? So that if I integrate it, I'm going to get the total energy. Okay, so maybe I'll write it over here in English. This is going to be energy in the cavity with omega between omega and omega plus d omega. Okay, so it is some sort of energy density per frequency. And now if you look at this, okay, expression and try to see what's going on, you see for small values of omega, there will be a cancellation of the constant term. This will be proportional to omega. It will cancel one of the omegas in the numerator. So it will look like something, okay, as a function of omega. If I call this thing rho omega, okay, I'm going to give it this name, rho omega. It will start quadratically, okay, it will start as omega squared, but as omega becomes larger and larger, okay, it will eventually be killed, okay, by e to the minus h bar omega over kBt. Okay, so this can be plotted in terms of the wavelength, okay, lambda, which sometimes is more useful because experimentally people want to use the wavelength rather than the frequency, okay? But it has a shape which goes like this. Obviously, if you increase the temperature, you are going to get higher and higher energies, which means you are going to get curves which go like that, okay? So this is going to be higher temperature, lower temperature on this side. So this was one of the earliest successes of quantum theory. People just assumed that the harmonic oscillators had quantized energies, which went like multiples of h bar omega, or the photon had energy h bar omega, so that the interpretation was that you either had one photon, two photons, three photons, etc., per energy state. Okay, so it said something like there's 0 photon there, so there's 0 energy. If there's 1 photon there, then there's energy h bar omega. If there are 2, okay, that's what we are doing. We are multiplying this nk with h bar omega. Okay, so number of particles times h bar omega, because we said each particle had an energy, each photon has an energy h bar omega. But we have swept something under the rug. Okay, and what is that? We said that this came from an analysis of harmonic oscillator discussion. So the energy is not equal to really n times h bar omega. What is it equal to? N plus 1 over 2 was the measure. So let's make a small correction there. Okay, so the internal energy is going to be equal to, okay, so I'm just going to rewrite the same expression, nk ek, okay, times this factor, which was, okay, so this is, I write it so many times and I still forget it, k squared dk over pi squared, and there's a volume factor, right? So let's put it over there. Did I miss anything this time? I think I'm okay. All right, so I have something like this, and I have to integrate this over all k from 0 to infinity to find the internal energy. But this ek is now something like h bar omega times nk. Okay, so what I should do is over here, I should put in the average value of nk. So how do I do this? So I'm going to replace this with h bar omega nk, number of particles. Okay, number of particles means the energy state of the harmonic oscillator plus 1/2, okay, times k squared dk over pi squared v, and I still have to integrate it 0 to infinity. But now you see what happened. This is my original term, so I'm going to get h bar omega, and this nk is 1 over e to the h bar omega over kBt minus 1, so that's that piece. But I have 1 over 2, and I have to translate this into omega, so it's going to be omega squared d omega divided by c cubed, right? And divided by pi squared v. In any case, you don't have to go very far. You see what's happening to this second term. What will that give me?
Constant? No.
No,
Not constant, absolutely.
it will give you infinity. Okay, so this is called the 0-point energy. And it seems to be infinite. So in order to kill one monster, the classical equipartition theorem, we obtained a very nice experimentally consistent result, but we created another monster. Okay, so that's an infinite amount of energy, 0-point energy, which says that if you are discussing a quantum mechanical oscillator, that is going to have a 0-point energy. Okay, so there's going to be this h bar omega over 2, which is going to be present in each harmonic oscillator, even if there are 0 photons. Even if there's a 0 photon for any electromagnetic mode that you have, in these k objects. Okay, so I'll draw it one more time. So this is kx, ky, kz. So each one of these things is a harmonic oscillator. And 1 photon means first energy level, 2 photons means second energy level, and so on. But they also have an n equal to 0 state with h bar omega over 2 energy. And you have an infinite number of them. Okay? All of these things, even if they are very high energy, their h bar, even if they have very large omegas, they are going to have a 0-point energy associated with them. Okay, so this can be handled by various mathematical tools, in quantum electrodynamics by using a method called renormalization. But what happens is that whether it is real or not, it is some matter of discussion. But you see, it was so a scientist with the name of Casimir calculated the amount of energy that you would have with standing waves between two parallel plates. And obviously you have these modes. Again, it's a different counting, one-dimensional counting, but it's still some sort of counting. And although you are going to get an infinity, if you just change the distance between the plates just a little bit, it's a little different infinity, So you subtract one infinity from the other infinity and you get something finite. So this is something obviously which terrified people like Pauli, more mathematically inclined people. But you get a Casimir force, which is the change in the total energy as a function of the distance between these boundaries. And this is a measurable force. So this is something that can be measured experimentally. It's not very strong. You have to go to sub-millimeter distances for this to be detectable, but it is something that has been well studied. It's shape dependent. You have parallel plates. The force is attractive. If you have two spherical surfaces, then it becomes repulsive. Just because the shape of the boundary and the standing waves that you try to generate between these boundaries. So we'll have to work a little bit more on the on these counting the levels stuff, but that will have to wait until next time, which is Friday. Yes.